Swayam Prabha. Digital India. Educated India.
In this lesson, we will look at how to systematically analyze op-amp circuits. Now, if the op-amp is not ideal, it will have a finite gain, and then the analysis is no different from what we have discussed earlier for circuit analysis when the circuit has control sources. Okay? Because let us take the same circuit we have been considering. And let us say A naught is finite, that is, the op amp is not ideal. Okay. So, then the only thing different between this and all the circuits we analyzed before is the symbol. All we have to do is replace the op amp with a voltage controlled voltage source of gain A naught. Okay. So, my circuit becomes this. This is V D, this is A naught V D. Okay. So, now we have this control source and we know how to handle voltage controlled voltage sources. We have to basically replace the voltage controlled voltage source with a super node, and we will lose one equation. We cannot write KCL at this node. We replace that by the equation governing the voltage controlled voltage source. Okay. So, in this particular case, we cannot write an equation, a KCL equation at this node. Let us say if we are doing nodal analysis, but we can do it at this particular node, and then we use the control source equation, which is V naught equals A naught times V D as the extra equation. Okay. So, we have already discussed how to do nodal analysis with voltage controlled voltage sources. We also know how to do mesh analysis with voltage controlled voltage sources. So, this is not a difficult thing at all. Okay. In fact, with non-ideal op amps, the analysis is easy. It is the same as analysis of any circuit with voltage controlled voltage sources. Okay. Now, as far as analysis of ideal op amp circuits is concerned, now we cannot use the previous approach, because for an ideal op amp the gain A naught is infinite. Okay. If we have a multiplying factor which is infinite, we can't write legitimate equations. Okay. So, what we do then is the following. Again, the problem is that we do not know what is the current at the output of the op amp. Okay. If I call this IOPA, IOPA is not known. Okay. That is, it is unrelated to the characteristics of the op amp. We cannot write some equation based on what the op amp is. This is similar to how when we had voltage sources either independent or controlled, we could not write an equation for the current through the voltage source from the property of the voltage source. Okay. So, that is determined by what is connected to it. So, we replaced it by some other equations. So, in case of the ideal op amp also, we will not be able to write KCL equation at the output node of the op amp. So, instead we have to use the virtual short equation. Okay. So, this is V 1 and V 2, V 1 equals V 2 and this corresponds to the virtual short. Okay. So, bottom line is KCL equation cannot be written at op amp output. So, for each op amp, so far we have been considering only circuits with a single op amp. If you have multiple op amps, the principle is the same. So, the KCL equation at the op amp outputs is replaced by virtual short equation for that op amp. Okay. So, that is the way we analyze op amp circuits in general. Okay. Now, you have to always keep in mind that this virtual short applies only if the op amp is in negative feedback. That has to be checked separately using ideas we have discussed earlier, that you have to check that every op amp is in negative feedback, but once it is in negative feedback, the inputs are virtually shorted and you can use this for analysis of circuits with ideal op amps. Okay. So, just for completeness, let me analyze this circuit. We already know the result, but I will systematically put down the nodal analysis equations. Okay. So, now we have an ideal op amp and there are 3 nodes 1, 2 and 3. Now, we will try to do nodal analysis, which means that we should try to write Kirchhoff's current law equations at all the nodes. The reference node of course is the ground. Okay. This is the reference node. Now, if you look at node 1, there is a voltage source there. So, that means that we cannot write KCL equation over there. Okay. Instead of that, we have to essentially write the constraint for this voltage source. What you do is you form a super node with node 1 and the reference node. Because you do not write any equation for the reference node, you can't write any equation for this super node either. Instead of that, you simply have the constraint imposed by this voltage source, which says that V 1, the voltage at node 1 equals V I, the source voltage. Similarly, 2, you cannot write a KCL equation. This node is connected to the op amp output. So, we do not know the current flowing out of the op amp. So, no KCL equation there. Instead of that, we write the virtual short equation. What does the virtual short equation say? It says that this node voltage and that node voltage are the same, that is V 1 equals V 3. Okay. And finally, at node 3, we can write the KCL equation. Okay. So, that is V x, which is the same as V 3. So, let me use my usual notation, which is V 3 times the sum of conductances, which is 1 by R plus 1 by k minus 1 times R, okay, minus V 2 1 by k minus 1 times R equals the total independent current source being injected into this node, which is 0. Okay. So, if I solve with these 3 equations, this one, that one and that one. So, essentially I will get the solution, which is that V 1 equals V I, V 2 equals k times V I and V 3 equals V I. Okay. So, this is the solution to these 3 equations. So, if you have a complicated circuit with many op amps, again you cannot write Kirchhoff's current law equations at the op amp outputs. So, you forget that, you instead write the virtual short equation for that particular op amp. Clearly, this method applies only when all the op amps in the circuit are in negative feedback, which has to be checked separately. Okay. So, then you will have as many equations as you have unknowns. If you have other voltage sources in the circuit, you have to use the supernode concept. I am assuming we will do nodal analysis, but whatever we discussed for mesh analysis also applies here. Similarly, if we have controlled voltage sources, then we again have to form supernodes and so on. Okay. So, everything else remains conventional. The op amp, the equation at the output node is replaced by the virtual short equation at the op amp inputs. Okay.